Very good evening to all of you. Today we are going to discuss various applications of matrix algebra in the domain of machine learning. And in this present session, I will discuss around 8 to 9 applications of matrix algebra in machine learning. And the remaining topics will be discussed in the next session. And here, the usefulness of matrix algebra in machine learning has a lot of applications, and it is the major fundamental mathematical concept, and it plays a crucial role in various aspects of machine learning. If you look at the applications of ML, are data representation, linear transformation, matrix operations for model training, principal component analysis, which is popularly called as PCA, and singular value decomposition, SVD, and convolution neural networks. So these are the topics in which the matrix algebra applications we are going to discuss. And the first topic is data representation. The data can be stock market prediction, and another is any data what we can consider as a student data, as a basic one I am representing here. The student number, student name, and marks. These are the three columns we are going to have, and there are three other rows which are called data points. Each row is called a data point, and whole matrix we are calling it as a data set, and which is represented in the form of tabular form. And each column is called the feature or attribute. Here the three attributes names are student number, student name, and marks. And tabular representation is the efficient storage of data, and we can manipulate the data also when it is represented in the tabular form. And the second application, what I am looking at, is linear transformations. So in machine learning algorithms, most of the applications are in the form of linear transformations of the data. And one of the example for this is linear regression model, in which matrix enables the relationship between input features and output labels. So input features and output labels means that is target variable, and these are input variables we can consider also. So in a linear regression, which is of the form y equal to mx plus b, that is the simplest form I'm considering for our discussion. So x is the input variable and y is the target variable, that is output label we are looking at. And here m and c are the coefficients we are considering, coefficient and constant. So here the matrix algebra is used to solve normal equations in order to find the coefficients which will best fit a linear model for the given data set. I can show you an example of a data set, so where the heights and weights of the people are given, and we are going to develop a best fit linear regression model for the data set, so that we can predict for not given some height value which is not given in the table, for which the weight of the candidate can be able to find in a better way. So matrix multiplication will do the transformations, and to be performed efficiently the transformations. So the example what we are going to consider here is, suppose height and weights of few students I have given. So a student with 120 centimeters height, his weight is 50 kilograms, and 140, it is 70. Like so, we have given almost 7 data points here. Now what I am doing is, I am developing a linear transformation model for this. The linear transformation, the data is in the tabular form, we brought it into the linear form. This is something like y equal to mx plus c. So the c is the intercept form, and this is a y-intercept, that is minus 43.580 and so on. And this is m, the slope of the equation. So These two are the coefficients we are finding from the normal equations by solving the normal equations. And this is the height we are considering, and this is the weight. Suppose height is x and weight is y. So this is the input variable, and this is going to be the output variable. Here, I used some Python code and for the linear regression model and predicted the values which are not there in the given height column. So 130 is not there in the given column. So for which the weight will be 59.58 roughly. And the height for 145, which is not given here, I have predicted the value is 71.48. Like that, the weights are going to be predicted. So by bringing this into the linear transformation, linear regression model, this is the one beautiful application you can see. This is how we can manipulate the data, which is represented in the matrix format. Another is that is data representation, what we are going to what we have discussed so far in the gradient descent. So this is also what we have discussed as a part of the calculus, but internally if you look at the matrix operations for model training. So during the training of the ML models, matrix operations, if you look at the calculate the gradients and update the model parameters. So using these matrix operations, what we are going to do, we can calculate the gradients of the ML model and update the model parameters so that the model parameter, ML model parameter performance can be enhanced. So gradient descent. So it is a matrix calculus to optimize the model performance. So it is in part of optimization technique. So we are using with the help of matrix operations. We are optimizing the machine learning model performance and training ML models. Gradient descent and its variants involve matrix operations, and what we are going to do is update the model parameters and minimize the loss function so that the ML model will be more efficient compared to other models when we are taking into consideration of gradient descent. And another is principal component analysis, which is popularly known as PCA. So the dimensionality, the principal component analysis is useful for the dimensionality detection. What is dimension? Again, I am saying here the dimension is nothing but the number of, the dimension is an attribute. The dimensionality reduction means number of attributes we are going to reduce. Suppose a data set consists of around 50 or 60 attributes. Okay, so it is not possible for us to to manipulate the data set, and it is more it is taking more time, and we can say the time complexity of that algorithm is going exponentially sometimes. So that's the reason we are going to reduce the number of attributes. So that approach is called dimensionality reduction techniques. And another way we can call it as feature extraction. So the required features only is extracted from the total number of features. So for this, what we are going to use is eigenvalue decomposition for a given covariance matrix. The data set is represented, which is in the form of numerical representation. So which is represented in the form of covariance matrix, and over which the eigenvalue decomposition is performed. So we are going to find the eigenvalues and eigenvectors. With that, we are going to develop a eigen matrix, and the matrix decomposition we are going to do to find the principal components of the data. So here, the principal components of the data, that means we are decomposing, means here we are reducing the matrix size further. So the matrix operations here, what we are going to use is eigenvalue decomposition or singular value decomposition. So this is how the PCA method goes ahead by application of matrix operations or matrix algebra applications, we can call it as. So the singular value decomposition, it is also called matrix factorization techniques, which is used in various machine learning applications. So certain applications are mentioned here as the recommender systems. So which I discussed in uh, Amazon. So if you purchase certain product, it is showing some other recommendations. Am I right? So recommender systems we use this, and data pre-processing we can use, image compression we can use. So like this various approach, I mean applications, the singular value decomposition is very much useful. So image compression, I can consider it as a totally a different domain where lossless compression and lossy compression, there are various techniques are there. But one of the image compression techniques, image compression model is JPEG. So decomposes a matrix so into three other matrices. So reducing by which we can reduce the noise and capture the essential information for further processing. So this is how the matrix algebra is useful in singular value decomposition. Now we will look into the convolution neural networks, popularly known as CNNs. So if you want to, it is a one of the techniques used in deep learning and which is use convolution operations, and it is viewed as a form of matrix multiplication when applying filters to the image for feature extractions. So here if you want to identify the face recognition, one of the example I'm saying. So object recognition. So CNNs are very much useful, which comes under part of the deep learning models. And convolution layers. So uses CNNs apply convolution filters to input data using matrix convolutions. So in this way, the matrix operations are very much useful even in CNNs. So the summary, what I can say is the matrix algebra and matrix operations are very much useful in the machine learning, particularly the today's topics what we discussed is data representation, linear transformation, matrix operations for model training, and principal component analysis, singular value decomposition, and convolution neural networks. Thank you. Uh, I wish you good luck and please subscribe, and any further queries we'll discuss in the below link. Thank you. Thank you one and all.